All right, so next up, we're going to talk about kinetic molecular theory. And so this is the kind of model that we've been talking about, the model of our ideal gas. And no gas is truly 100% ideal, but most of them under kind of quote unquote normal conditions are pretty close to the ideal gas. So it's very useful. And so this is going to provide our why behind our PV equals nRT. So let's take a look at the first thing that we assume. And again, we're in our little container here. And now I'm just going to draw the gas molecules as these tiny little dots. And so that's kind of one of the assumptions that we make in this kinetic molecular theory. And it's pretty good most of the time. And that this space is so large that atoms are of negligible size. So basically, we just assume that the atoms take up essentially no volume just because they're so tiny relative to the space in between them. So for example, if you're at standard and temperature and pressure, if a molecule were the size of a golf ball, the nearest neighbor would be 4 feet away. So you can see they're not really pushing up against each other, so they practically have no volume. All the volume comes from the pressure exerted by them bouncing around. The second thing is that when we increase temperature, what we do to these molecules is increase the kinetic energy. And so essentially we kind of make them go faster. We'll see that it gets a little bit more complicated. There'll be another video kind of specifying this section right here. But for now, we're just gonna say as we increase the temperature, our gases move faster and faster. And then the third assumption is that all collisions are elastic, right? So if we have some kind of gas molecule and they're both headed in the same direction, they're going to kind of collide with each other right here. And we're going to say that they bounce off elastically. And so what that means is that there's no overall loss of energy. Think of it like an ideal pool situation, right? If you're playing pool or billiards, right? You hit the ball, you hit another ball, and basically the overall energy is somewhat, not lost. There's no overall loss there. A different example would be like a car crashing into another car. Both cars would stop. That would not be a elastic collision. And so the other thing that we're kind of assuming with this elastic collision is that there's no attraction between the molecules. And later on, we'll label that as intermolecular forces, and we'll see how intermolecular forces play an important part in solids and liquids, but not so much in gases. Right, so these kind of three ideas are kinetic molecular theory, and they kind of explain this PV equals nRT relationship. Right, so one of them is that pressure is inversely proportional to volume. As one goes up, the other goes down. So you think of this as volume. When volume increases, pressure is equal to kind of a force over an area. And so if you're increasing the volume of something, you're increasing the surface area. And so if you think about a number that's equal to 1 over a number, as the denominator grows, P is actually going to shrink. And so we've already kind of been working on all these things. I'm just explicitly stating them here. So more area, same number of molecules. Less collisions per area, and so less pressure. Cool. Another one of the things we say was that temperature is proportional to pressure. Yeah, both of those are terrible. So as temperature increases, right, we're moving faster. Molecules have more kinetic energy. So we hit the walls harder. So what we're doing is increasing the force, and so they'll be directly proportional, so pressure increases. And then finally, when we increase N, when we increase the number of moles, we have more gas hitting the walls, so more pressure or more volume. Right? Depends how strong your walls are. Or maybe a little bit of both, right? A combo of both. And we've been working on these ideas, so nothing really new here. There's just a picture of these. So you can see here, temperature, increasing temperature. We're going from here to here. Basically, they're showing that these molecules are hitting harder, right? So they hit harder, so we increase the pressure. And then you just pause and take a look through these and explain them through yourself.